Sir?
Yeah?
I'm using a different device than what I usually use, so I can't figure out how to use the chat.
Okay, it's all right. I can see. I'll just...
All right.
Thanks, Will. Okay, so we got 14 people, but we're supposed to have another dozen or so on top of that. So I'll just give them another minute or so to see if they get in. Okay, while we're waiting, attached to the Google Classroom post for today's lesson is this handout. So it would be really helpful if you had that up in front of you on your computer. You don't have to. I'll be showing it on the screen anyway, but sometimes it's easier to see when it's your own document rather than getting it a kind of fuzzy copy through the video. So that's attached if you've got it. Okay, I don't think maybe anyone else is coming, so we'll make a start, I think. Yeah, just pulling the PowerPoint up. Okay, let's make a start. So remember, if you want to toggle between the video and my screen that you're sharing, just tap on the little one. So at the moment, my video is probably quite small, and you've probably got a big picture item on your screen. You can flip between them by tapping on my video feed, and that'll make the video big and the PowerPoint small. Okay. So far, what we've been talking about is the alpha, the beta, and the gamma radiation. So we have focused on what they are, what they do, how we can tell them apart, what they're useful for, how they're dangerous. But we haven't actually done anything other than talk about the alpha, the beta, and the gamma. And what we've been ignoring is the atom that gets left behind. So there's a perfectly good nucleus that is brimming with loads of protons and loads of neutrons. There it is on your screen. And what happens when the atom decays is just a small piece of it leaves the nucleus. So in this particular case, if we think about alpha decay, what we get is that there's all those protons and neutrons in the nucleus of the atom, and just 4 of them leave. 2 protons, 2 neutrons, a little bundle of 4. That's all that happens. And the rest of the nucleus gets left behind. But it's not the same nucleus that it was before, because it's now 2 protons down and 2 neutrons down. So it's not the same as it was. And today's lesson is about what that means. What does happen to the nucleus that we leave behind? Okay, so what you're going to need for today's lesson is this booklet that is a PDF that I've attached onto the Google Classroom post for today. Now, I don't expect you to print this yourself. You're welcome to print it if you want to have one in front of you, but it goes on for 8 pages. And I've got loads of these in the classroom ready to give you this lesson. You're just not here to have them off me. So when you come back into school next week, I will give you this booklet. But there's bits that you need to fill in. So there's fill in the gaps bits. And I need you in the back of your exercise book today to just scribble down what goes in the gaps, so that when you get this booklet off me next week, you can fill it in then. So just get a pen and turn to the back of your book and just scribble a title to yourself so you remember what it is, that it's the answers to the booklet that you're going to get next week. So we're going to start by filling that in now. You're going to scribble it in the back of your book. So let me just switch screens. Okay, so you can see the booklet now. So if I just scroll down to the first bit of it, right, it's going to talk about alpha and beta, but we're just going to start with alpha at the beginning. So just focus on the top picture. There's a big nucleus full of protons and neutrons, and a little bundle of 4 leaves, 2 protons and 2 neutrons. So just have a little look at that first sentence. What do you think goes in the gap? It's a number first and then a couple of words after that. So an alpha particle removes something protons from the nucleus, and it also removes something else, but that doesn't affect which element it is. I'm going to give you 30 seconds, and then I want you to give me an answer, please. Okay, who wants to give me an answer? An alpha particle removes, just unmute yourself and shout it out. An alpha particle removes.
Is it 2?
Okay. Yeah, it is 2. So we've got a couple of 2s and a couple of 4s. It's 2 protons from the nucleus. So scribble a 2 in there, well, in the back of your book, so you can put it in next week when we get it. An alpha particle removes 2 protons from the nucleus. It also removes what else? What else gets removed at the same time? Take a look at the picture.
2 neutrons.
2 neutrons, good. Hello, Harley, you've turned up. That's good. So scribble it down. An alpha particle removes 2 protons from the nucleus. It also removes 2 neutrons, but we're not very interested in that. Okay, so what's happening here when we remove 2 protons is that it can't be the same nucleus anymore, because whatever nucleus it was before was determined by the number of protons that there was. And we've just lost 2 protons, so it can't possibly be the same atom anymore. So what we need to look at is what atom is it? Okay, so if I scroll down the page a little bit, and we'll see an example of this. So what you've got in the middle of the page looks a bit complicated, and I suppose it is, but we're going to unpick it in baby steps so that it doesn't seem too complicated anymore. So what we're looking at is a big nucleus. The chemical symbol of this nucleus is Rn, and that stands for radon, which is a gas that kind of leaks out of rocks and it's just part of the air. So some of the radon atoms are completely harmless, but 1 or 2 of the radon atoms in any particular sample are going to be an isotope of radon that has 219 protons and neutrons in its nucleus. Now, of that 219, 86 of them are protons, and all the others are the neutrons. So 86 protons, 219 altogether. The radon is now going to change into something else. It's going to decay. So that arrow in the middle of the page, we would pronounce that as decays into. So decays into. And what's it going to turn into? Well, there's going to be an alpha particle, because that bit comes flying out. And the alpha particle is always made up of 2 protons. And because it's got 2 neutrons as well, 4 particles altogether. It is always a 4 and a 2. And you need to remember that for the rest of the course. It's always a 4 and a 2 whenever it's alpha particles. So the question is, what else is left? Well, there were 219 things in the nucleus, but 4 of them just left. So 219 take away 4 is 215. And 86 of them were protons, but 2 of them left. That only leaves 84 behind. Now, if this was a chemistry test, they'd then make you look up in a periodic table what element 84 is. But this is physics, and we couldn't care less about the periodic table, so we're not going to make you look it up. But if you did look it up, you'd find out that it was element polonium, PO. Okay, the physics bit that you need to be able to do is the numbers. So you need to be able to work out that 219 take away 4 is 215, and 86 take away 2 is 84. Okay, I want you to have a go at a couple yourself. So what I'm going to do is scroll down to some questions. So if you can see those 4 questions on your screen. Hi, Reese. And Elle. And okay, so what we need to do, copy this, this way that we did it, where you take that number off that number, and that number off that number. I need you to try it for these 4 questions. What I'm going to do is I'm just going to give you 30 seconds to have a go at question number 1, and then I'll go through question 1, and then we'll have a little bit longer to do questions 2, 3, and 4. So just have a go at question number 1 yourself now. What are the 2 missing numbers? 30 seconds. Yeah, just do it in the back of your books. Because, like I say, I'll give you this handout and you can fill it in when you get it. So just scribble the answers in the back of your book. It is hard, Harley, but don't worry. We're going to take it in baby steps and it'll be all right. A couple of you have turned up while I've been talking. Just shout out if you're here. Save me going back through the chat. El Booth, Izzy Collingwood. I'll stick it on the chat again. Kayla Fletcher, Tom James, Isla Lancaster, Carly, Jack, Zach. Any of you here? Pick another shout out on the chat if you are.
I'm here.
Thanks. Sorry, who just said I'm here?
Holly.
Hi, Harley. Thanks. Okay, let's have a go at the first one. So it's an atom of uranium. That's what the U stands for. And uranium's got 238 protons and neutrons altogether, and 92 of them are protons. It's going to lose an alpha particle. Tell me what numbers we always write for an alpha particle. Shout it out. Or write it on the chat. Yeah, 4 and 2. Thank you. Always 4 and 2. 2 protons and 2 neutrons. 2 and 2 is 4. And 2 of them are protons. Bottom number's protons, top number's the total. So all you got to tell me is what's left. So there were 238 of them. 4 of them left. So how many got left behind? Stick it on the chat or shout it out.
234.
Thank you very much. And then, of those, 92 of them were protons, and 2 of them left. So how many got left behind? Yeah, that's right, Max. Thank you very much. 90. And again, you wouldn't have to look this up in a periodic table. They'll always give it to you. Element 90 is TH, which stands for thorium. So 90 and 2 is 92, and 234 plus 4 is 238.
So why has it changed to TH?
Because uranium is what is the name of the atom that has 92 protons. So 92 means uranium, and uranium means 92. Remember, this is the atomic number, and it tells you which element you're talking about. So in physics, we like to give the elements numbers. In chemistry, they like to give the elements names, but it means the same thing. If you say uranium, I say 92, and if you say 92, I say uranium. It means the same thing. So once it gets rid of a couple of protons, it's not allowed to be called uranium anymore, because uranium's an atom that's got 92 protons. The atom that's only got 90 protons is thorium. So what we're saying here is that it changes into a new element when it decays. It loses a couple of protons, and so it's not itself anymore. It turns into something new. So that's why it's got a new name, because thorium is the element on the periodic table that has 90 protons, whereas uranium is the element on the periodic table that's got 92 protons.
Probably the most confusing.
Okay. It is confusing, isn't it? It is.
Yep.
Okay, we're going to try the other examples, and then I'm going to go through them with you. The key thing to remember is it's always 4 and 2. So although there are some blanks on your page next to alpha for question 2, you just write in 4 and 2 because it's always 4 and 2. And then when we get to questions 3 and 4, suddenly the alpha's disappeared and we've replaced it by HE. But if you remember, we only called it alpha when we didn't know what it was. But then later on, we discovered that alpha was actually exactly the same as helium. So sometimes you'll see it written as alpha using its old name, and sometimes you'll see it written as helium using its new name. You can use whichever one you want. So I've given you some questions. The first couple use alpha, and the second couple use helium, but it's the same thing. And it's still 4, and it's still 2. Right, have a go at filling in questions 2, 3, and 4. And I'll give you, 30 seconds for each one? And we'll see how we go after that. Give you 90 seconds. Have a go. Hold on, Chloe. Hang tight. Another minute for everybody else. Okay, let's go through questions 2, 3, and 4. So you might want to make the video big by tapping on it so you can see the board properly. Okay, first things first, it's always 4 and 2. So the first thing you should have done is gone down your page and put all the 4s and all the 2s in. It's always 4 and 2. 2 protons, 2 neutrons. The bottom number's the proton, top number's what it is altogether.
Why is helium 4 and 2?
Okay, so remember, we called this little bundle of 2 protons and 2 neutrons, we called that alpha when we needed to give it a name and we had no idea what it was. So we just called it, oh, that type of radiation, we'll just call it alpha. Alpha, remember, is the first letter of the Greek alphabet. So alpha, beta, gamma is like saying A, B, C if you were Greek. So what we're saying is this is like type A. And we called it type A, type alpha, when we didn't know what it was. But then later on, when we did know what it was, and we went, hey, hang on a minute, it's 2 protons and 2 neutrons, that's exactly the same as helium. So after we learned what it was, we can give it its real name if we want to. It's like that program that I can't stand on TV where those singers sing in a funny costume with their heads all covered up and you don't know who the singer is, so you might call them the chicken or something like that, or the hedgehog. But it's just a nickname until you work out who it really is, and once you know who it is, you can use their real name. Well, alpha's just kind of like, we don't know what it is, so we'll call it alpha, but afterwards we learned that it was called helium, so we called it helium in some of these questions. So you can use alpha, or you can use He for helium. It's completely up to you which you want to use. Is that right? Okay.
Yeah.
Okay, so what we're seeing is uranium turns into thorium. This is radium, and it turns into radon. This is lead. I don't know why it's called Pb. Lead turns into mercury. Don't know why that's called Hg either. And thorium turns into radium. So that's the chemical bit that's going on, but we're focusing on the numbers. So somebody want to tell me what numbers go here? So there were 226 protons and neutrons, 4 of them left. How many got left behind?
222.
Very good. And of those 226, 88 of them were protons, but 2 of those left. So how many protons got left behind?
86.
Perfect. Okay, let's look at the lead. There were 210 protons and neutrons. 4 of them left. How many got left behind?
Uh, 206.
Brilliant stuff. And of those 210, we had that 82 of them were protons. 2 of them left. How many does that leave behind? That's correct, Hugh. Thank you very much. So we got 80, and Izzy, thank you. Okay, so 80 protons left behind. Right, question 4 is a little bit different. We've been given the answer and we need to work backwards. So there are 4 protons and neutrons there, and there are another 226 there. So how many are there altogether? Yeah, 230, thanks very much. And then of those 230, there are 2 protons there and 88 protons there. So how many protons have we got altogether? Yeah, that's right, Hugh. Thank you very much.
Sir,
Yeah.
isn't the number 4 beginning thing the same as the number 1 ending? So why are they different?
Good question. That is what I am going on to next. Good observation. Okay, there's a couple of little things on the board like that that we need to talk about. So let's start there. This is thorium, proud owner of 90 protons. And this is thorium, proud owner of 90 protons. But the number at the top is different. Now, the number at the top is the number of protons and neutrons. And that one's got 4 more. That one's got an extra 4 particles compared to this one, but the protons are the same. So it can only be the neutrons that are different. So this one has got 4 neutrons more than this one. But remember, we don't really care about the neutrons very much. They're there as glue holding the protons together. What we really, really care about is the protons. So some atoms of thorium have got 230 protons and neutrons, and some atoms of thorium have got 234 protons and neutrons. As long as they got the same number of protons, they're still thorium. We don't really care if there's a few more neutrons or a few less neutrons. It doesn't make a difference to what we're doing on the periodic table. It's still thorium. The protons are what count. We used a word for an atom that has the same number of protons but a different number of neutrons. Can you remember what word we used? It begins with an I.
Is it ion?
No, we did use ion, but that's not this word.
Is there an isotope?
Isotope, brilliant. So that and that are isotopes. Just means different versions. So they're different versions of thorium, different isotopes of thorium. One's got 4 more neutrons than the other one. Okay, good question. Also notice on the board, we got some radon there. Sorry, radium. And we got some radium there. So the thorium gets rid of an alpha particle and turns into radium. And then the radium gets rid of another alpha particle and turns into radon. So sometimes radioactivity just goes on and on and on. We start with one radioactive thing and it spits out some radiation, but then it turns into something that spits out more radiation. And that can turn into something else that then spits out more radiation. So it doesn't have to stop here. That's what I'm saying. It doesn't have to stop there. It can go on and on and on and on. And stuff can be radioactive for a long, long time because of that. Okay. Although it looks complicated with letters and numbers everywhere, when you drill down into it, all you are doing is kind of year 4 adding up. So 4 plus 226 is 230. And 2 plus 88 is just 90. That's all that you're going to have to do from the physics point of view here. You won't have to worry about what these things are called. You just have to do the numbers bit. So the numbers bit are, remember that it is always 4 and 2, and then just make these numbers add up to the same as that number. And the point of it is to demonstrate to you that the thing you started with turns into something else when it spits out the alpha particle. Okay, I'm going to stop talking for 30 seconds or so. I'm just going to let you have a look at that and make sure you're happy with it. And if you have got any questions, just unmute and ask them. 30 seconds. Okay, have a little look at the screen that I'm sharing again. So there's the slide that's got the alpha particle on it coming out of the nucleus. So we've talked about alpha. We now need to talk about beta. What happens when a beta particle leaves the nucleus? What gets left behind? Is it like this, or is it something different? So the problem, if you remember, with beta particles is that a beta particle isn't a proton or a neutron or a bundle of protons and neutrons. Flick back in your book, or maybe you just remember, what is a beta particle? We called it beta when we didn't know what it was, just like we called it alpha when we didn't know it was a helium nucleus. We later found out what beta was. So do you remember what beta is? Someone's got there. Thank you, Izzy. Yeah, an electron. A beta particle is an electron. Now look at that picture on the screen. Do you see any electrons? The nucleus is a big bundle of protons and neutrons. There are no electrons in there. So where did the electron come from? Right, here's your picture. What that picture is showing you is that one of the neutrons turned into a proton and an electron. Like it was wearing fancy dress or something, and it's whipped off its false moustache, and actually there all along was a proton. Who knew? And you can think of the electron as like the false moustache that it throws away that goes flying out of the nucleus. So it's not really true that a neutron is a proton and an electron. It's a neutron. It's a thing in its own right. But a neutron can turn into a proton and electron. So there's your little bundle of protons and neutrons sitting there in a big ball, making up the nucleus. And then one day, one of the neutrons just decides, you know what? I'm fed up being a neutron. I'm going to turn into a proton and an electron instead. And that's what it does. So the proton, unfortunately, gets left behind. It's in amongst the nucleus with all of its other proton and neutron friends, and it can't go anywhere. Remember, the neutrons act like glue. And as soon as the proton turns up, all the other neutrons in the nucleus glue themselves to it. And so the poor little proton can't go anywhere. Or maybe it likes it in the nucleus. Maybe it wants to stay there. But the electron, when it gets made with a huge amount of speed. And much as the electron is attracted to the nucleus, all of the electrons in the shells, remember, are attracted to the nucleus. Much as that brand new shiny electron is attracted to the nucleus, it just can't stay. It's been made traveling really, really fast. And it's just traveling way too fast to stay in the nucleus. And it just zips out of there before the protons can grab hold of it. So that's why an electron comes flying out, because it's just traveling too fast to stay. But the proton didn't get made with loads of speed, and all the other neutrons just glued themselves to it, and it got left behind. So you need to remember that in beta decay, a neutron turns into a proton. That's the key fact to remember here. A neutron turns into a proton. And if you're going to forget that, scribble it down now, that in beta decay, a neutron turns into a proton.
Wait, so write down beta turns into a proton.
No, sorry, a neutron turns into a proton. I know, there's all these words, aren't there? So the nucleus is made up of protons and neutrons, and one of those neutrons turns into a proton. And the byproduct of that is that it sends an electron flying out of the nucleus. And it's the electron that's the beta particle. And we called it a beta particle when we didn't know what it was. And then years later, when we got better machines and better experiments, we worked out that it was, in fact, an electron. So you can call it beta, or you can call it an electron. It's up to you.
Should I put neutron turns into a proton when it separates from the nucleus?
When it releases a beta particle.
Okay.
Because the neutron and the proton, they don't go anywhere. The neutron turns into a proton and the proton stays behind. The proton doesn't go anywhere. It doesn't leave the nucleus. It's just the electron that does, the beta particle. Okay, so back to what you're making a note on in the back of your book, ready to put in the booklet when you get it. The next sentence on the booklet says, a beta particle adds how many protons to the nucleus? When a neutron turns into a proton, how many protons did we get? Not a trick question.
There's one.
Just one, yeah. So a beta particle adds one proton to the nucleus, but at the same time we lost something. What did we lose? We lost two somethings.
Electron.
We did lose the electron, and what else did we lose? Two things. Lost the electron and a neutron turns into a proton. So we gain a proton, but we lose a
Neutron.
Yeah. So that's what goes on that line there. A beta particle adds one proton to the nucleus. It also loses a neutron. But that doesn't affect what element it is. So gains one proton, loses one neutron.
What was that, sir? You cracked up a bit.
Sorry. A beta particle adds one proton, and it also loses one neutron. Just make a little scribbled note to yourself, and then you can fill it in next week when you're back in school. Okay. Back to what's on my shared screen then. So there's an example. I don't know if you've got an arrow on your screen. When I look at this document, when I'm not sharing my screen, I've got an arrow after the C, but my computer's gone weird. And when I share my screen, the arrow disappears. So can you see an arrow after the C?
No.
Okay, I don't know why it's been eaten, but there's supposed to be an arrow after the C, just like there was before. So what we've got here is an atom of carbon. That's what the C stands for. And the carbon owns 6 protons. Carbon always owns 6 protons. If it doesn't have 6 protons, it's not carbon. And it also owns 8 neutrons. 6 plus 8 is 14. So 14 things altogether, and 6 of them are protons. So there's the arrow that should be there. And what's going to happen is that one of those neutrons is going to turn into a proton. So we used to have 6 protons, but we're about to get another one. So we're actually going to end up with 7 protons because a neutron has turned into a proton. So we gain a proton. But if you've got 6 protons, you get to be called carbon. If you've got 7 protons, you're not carbon anymore. You're something new. So if you did have a periodic table and you looked it up, the element that is the proud owner of 7 protons isn't carbon. It's nitrogen. Now, the number 14 is the total number of protons and neutrons. Well, we used to have 14 protons and neutrons, and we still do have 14 protons and neutrons. We lost a neutron, but we gained a proton. So altogether, we've still got the same amount of stuff that we always had. So it's still 14. So when you do a beta decay equation, the only thing you need to do is make the atomic number, make the protons go up by 1. You just need to remember that. Just make it go up by 1. Now, that's completely fine as it is. But all the other things have got numbers on them, so we better add some numbers to make it work. So 14 plus something is 14. Well, 14 plus nothing is 14. So that's just a 0. 14 plus 0 is 14. And then 7 something makes 6. So we need to take away 1. 7 take away 1 is 6. Now, personally, I think that's really hard to remember, 0 minus 1. So I don't even try to remember that. I just remember that the protons go up by 1. That's what I remember. I just remember the protons go up by 1. And then I figure this bit out later just to make it work. And I think, oh, 14 and 14, they're the same, so that must be 0. And 7 take away 1 makes 6, so that must be take away 1. But maybe your memory is better than mine, and maybe you can remember that you, just like we always used to write, we always write 4 and 2 for alpha, we always write 0 and -1 for beta. See if you can remember it. Also, when we were doing alpha, we just discussed that you can write helium if you want to, because alpha is just what we called it before we knew it was helium. If you want to write beta as an electron instead, you can do that. We called it beta when we didn't know what it was, but now we do know what it is. It's an electron, so you can call it an electron if you want to. Whether you call it beta or you call it an electron, it's always 0 and -1. Okay, same thing again. I got 4 more practice questions for you. This time they're beta ones. I'll give you 30 seconds to have a go at the first one, and then we'll go through it, and then I'll give you a bit more time to go through the next 3. So 30 seconds, have a go at question 5. Okay, let's have a little look at question number 5 then. So thorium turns into element Pa, which is actually protactinium. Good word. Okay, so thorium turns into protactinium. All that happens is you gain a proton. That's all that happens. So all you got to do is make the protons go up by 1. So what are the numbers that I'm going to write on those lines? Just make the protons go up by 1. $234 and 91. Thank you very much. All you got to do, just make the protons go up by 1. Right, have a go at the next 3 questions. Just make the protons go up by 1. That's it.
I thought you meant to take away a neutron.
Oh, sorry, yeah. What I mean is, what do you change? So we're not going to change the top number. Sorry, you're right. We do lose a neutron. But in terms of what do we change with the numbers, we just need to make the bottom number go up by 1. That's it.
Okay.
Yeah, you're right. Okay, let's go through it. So let's fill in this one first. The betas. What number do we always write next to the betas? Just like alpha was always 4 and 2. What's the beta? Thank you very much. Now, 0 and -1. Always 0 and -1. See if you can remember that if you can. Okay. Rule is leave the top number alone, just add 1 to the bottom one. So what shall I write for this one? Polonium.
Wait, so why does it say -1?
Let me answer that question at the end. Let's do the numbers first, and then I'll have some examples to work with to show you. So fill this one in for me, and then I'll come back to the -1s.
84 and 214.
Correct. Thank you very much. Leave the top number alone. Just change the bottom number by make it go up 1. So what about the protactinium turning into uranium?
2, 3, 4, and 91. No, 92, sorry.
That's it. And then this one's been done for us. So we finished with 28. So what must we have started with?
27.
Good. And the top number doesn't change, so we'll leave that alone. So why is it -1? Because we just need these numbers to work in the sum. So 214 plus 0 is still 214. 234 plus 0 is still 234. 60 plus 0 is still 60. But what we need to do is lose 1 from this number. So 84 take away 1 is 83. 92 minus 1 is 91. 28 minus 1 is 27. So that's why there's a -1 there, to remind ourselves that we need to take 1 away. It's not that important to remember the 0 and -1. It's much, much, much more important to remember that the protons go up by 1, but the total number of particles stays the same. Okay. In chemistry, you call equations like these chemical equations. But this is talking about nuclear physics, what happens to the nucleus. So these are called nuclear equations. That's a lot of those. Go away. So these are called nuclear equations. They're a lot like chemical equations in chemistry. And when you do it in chemistry, you call this side of the equation the reactants, and this side of the equation the products. And you say that the reactants turn into the products. Well, we haven't really got anything reacting here, so we can't really call them reactants. But we do have a name for them in physics. It's a bit of a weird name. It's a bit sexist. So this side is always called the parent. So the carbon, the thorium, the bismuth, the protactinium, the cobalt, they're all the parent atom. And then it turns into the daughter. So really, the parent decays and turns into the daughter, which is a bit messed up. But I don't know why we use that language. It's just historical that we do. So the parent turns into the daughter. So if you see that language, what is the parent nucleus? What is the daughter nucleus? That's what it's talking about. And when we get back into class and you get your booklet, there's a space for you to write that in. Just here, it says we call the original nucleus the parent and the new nucleus the daughter. You think it should be like mother and daughter or parent and child, but I don't know. That's the way it is. Okay. We don't seem to have done very much today. We've only done 8 sums, but actually it's probably made your head hurt a bit because it's pretty complicated. So although it didn't look like very much when we wrote it down, actually, we've done quite a lot today. So well done for keeping up. If you are confused at all and you want to do a bit more reading to catch yourself up and iron out anything that you're confused about, I've attached to the Google Classroom post a double page spread from the textbook. So if you are confused, you can read through that, and then there are 4 more questions at the end of it. And what I've been saying to all my year 10 class, I've got 3 year 10 classes, what I've been saying to them this week is that I feel a bit tight setting your homework. I know lots of teachers are setting your homework, but you're sitting at home with a computer on your own all day for 5 hours, and it's a bit boring. And I'm sure the last thing you want to be doing is doing extra homework on top of that. So I haven't set you, I'm not going to set you any homework while you're isolating at home. But what I would say is, you're probably not getting 5 lessons a day. There's probably sometimes you only get 4 lessons or something like that. So if you do find yourself over the next week or so with a spare lesson where you haven't got anything to do in it, just come back to today's assignment on Google Classroom and have a look at that double page spread in the textbook and read through it. Make sure you understand it okay, and then maybe try the 4 questions at the end. And I've put the answers on the Classroom post as well, so you can check if you're right or not. And that'll just mean that when we come back to this next week, you're ready to go and you understand it as best you can. However, for today, well done. Hope your head hurts not so much. And it's the end of the day now, so I guess you get to quit. I'll see you next week.